Yo, 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 what's up, boo? Just setting things up here. Okay. There we go. All right. So, just 1 second here. God damn it. Okay, there we go. All right, let's see. Hello, hello, how are we doing? Okay. So, I've been doing a little bit off stream. I fixed the issue that we had where, yeah, there was some issue with the pipeline. Yeah, the basic pipeline, yeah. So this one, and this one now works. And the issue was that I forgot to update the instruction. I think it was like the pipe instruction. So the pipe instruction was, I think it was the pipe instruction. It was one of the instructions anyway. I forgot to update it to actually set the result register after it was executed. So yeah, then that actually fixed the issue. So if we run this now, we can see that it works very well, very good. What else? Yeah, I added also, like you can see to the right, I updated the debug window a little bit. So there, what you're seeing here is what you're seeing like as default is like the thread that's currently executing, the registers here, and here's like the a cutout of the instructions, and that we're currently on, and the arrow points to where we are going to execute next, and then the stack, which is empty at this point. But if I step, we go down here, and we get these 3 pipes on the stack here. And then if I step once more, it's gonna fork, and you can see the instruction counter is increasing and all that. And we get some more stuff happening. Yeah, so it just goes down the list here of instructions. And now we're on another thread, which is thread 4, which does other things. So, and then you can toggle what this will show by info. So now info will show a summary of all the threads, and then info again will turn it off, so that we kind of cycle through the things there. Okay, and did I do something else as well? I forgot. Wait. Just done the IO issue, fixed pop instruction. Oh yeah, it was a pop instruction, that's right. The pop instruction was missing the result register properly. So whenever we popped, it should set the register to be whatever we popped, but it didn't. So we got whatever was like previously the default. So that was messing things up a little bit. I'm not sure if I mentioned this, but I also added signal handling. So let's say we're in like a loop. So let's go to like cat, or well, let's do like infinite loop, or I mean cat infinite, and we just say cat, because when you just say cat, it's gonna wait for standard in. So if we run this, it's just gonna hang basically, and then don't produce anything. So if we go into the to the debugger here, and we type continue, it's gonna run forever. But if we interrupt, it's gonna say we received an interrupt signal, so it's gonna stop the execution. And if you press interrupt again, we go back to like the original handler, which is just to exit like the process. But I mean, we should probably have some other handler, but to like properly exit the thing. But yeah, that's good to have. Yeah, but I think that's probably it. Signal handling, memory stuff, yeah. So what I'm working on now is the heap memory. So I realized that because I was trying to do just like a very standard. So I was working on the bindings, and well, for this thing here is like, there's no problem in creating the data here. This is like read-only data. So this is bound to a read-only data location, right? But then if we want to use this here, for example, in this string interpolation expression, what's happening is that we have, I mean, in this case, we only have one segment. So it's kind of like, it could very well just be, optimized into just S at this point. But we don't. What I want to solve is the generic case for all of this. So let's say we just add, like this, for example. So what we need to do here is basically. So okay. So how this used to work, or how this works before, is that we store the string as a list of values, basically. And those values can be, it can be a location to a string. It can be another string, just a straight up literal, string literal, or whatever. And so, or anything that can be kind of turned into a string, basically. And so, but however, this is not really feasible to store as a value, really. So what I opted to do, and which would also like play into other things, is to start to work on like a heap allocated mechanism. So what that means is that in addition to the stack, and well, it's just the stack and read only actually. So we're gonna have the heap. So we're gonna be able to allocate things on here. So what this will turn into is basically we're gonna have the read only here. Never mind the weird errors showing up there. There's like a LSP issue. Yeah, I need to fix that. Well, actually it's compare. I'm not sure what's going on there. Okay. Anyway, so read only is just gonna be, hello, of course. And then you're gonna have whatever this is gonna, compile into. And basically it's gonna be, exec And what are we execing? Well, we're execing echo. So that's just gonna straight up go in there, which means that this is actually gonna be like echo hello or something like that. Or actually it's gonna be the other way around because of the ordering of things, but whatever. So we're pushing that. We also push at the last how many arguments into echo, which is 1. And then we push first argument here. So what is this first argument? Well, I'm thinking it's just gonna be, we're just gonna take the we're gonna allocate an array, and the array is gonna be kind of like what we had before. Like the array is gonna be a list of values, which is gonna be, the first is gonna be S here. So it's gonna be like the location to, so something that can be turned into a string basically. And then the other element is gonna be this. So this will become a list of 2 values, where the first is S and the second is that. So, and that is gonna get stored in a heap pointer. So what we're pushing here is gonna be a pointer to a string basically, or a pointer to a list of values. And actually it's kind of typed as well, because it's actually a struct actually. So it's a struct that is like runtime known. The type is runtime known basically, and well, it's kind of like a slice in Zig. So it has an address and a length. So what we're gonna have is like a pointer to an allocated of length 2, and then the length is 2. So that is what we're gonna have, this slice here. So this is gonna be like and then that is copied around as a well, it's a slice. It's like a slice in so we're gonna push some kind of slice here, and then what's gonna happen also, what's gonna happen is that we need to create this as well. So we need to, so we have now we have a new instruction called alloc, which allocates, and then the number of elements that we want to allocate. So it allocates to, and then it returns the result in our result register. Okay. So now we should have the kind of pointer. Well, or I think we'll have like the slice in the result register right now, because the result register can hold any type of value. So now we have the slice in the result register, and I think we simply just use that over here as a thing. So this would be like a slice of values basically. So this is kind of like, before we're using the term stream for this, but it's changed a little bit, because now we don't allocate in Zig, we don't allocate like an array of values. We are allocating it on the heap in runtime in the virtual machine now. So this is like pointing to an address, and it has a length. But then we know that the type of the things inside are going to be values. So we know how to kind of handle those and turn them into strings, so that we can kind of produce the final string value that we're going to call echo with, right? And then over here is like, okay, well, once we have this allocated thing, how do we actually put stuff into it so that we can now put these things on the heap? So for example, when I put this on the heap and this on the heap, But this part could be so this part is kind of easy because it's just gonna be compiled into a read-only data section. So actually we could add that here, and then so the second element will just point to this, and then the first element, well, it's going to be the expression that's inside here, which will also just refer to this here. So how do we then put things into this, into the thing? So basically what we're going to do is we need to set or, except it's going to be like or plus 0 for the first element. So this is really just, well, it's kind of different because this is kind of setting the, on the heap, we're setting the address here to whatever we get next, which is going to be, well, it's going to be like the read-only data. So I don't remember the notation here, but it's going to basically be, so the first one will be S. So that's hello. So 0 to 5 or something. 0, 1, 2, 3, 4, 5. Yeah. And then we're going to set the next one, which is going to be plus something. So plus 1, because each value always has like, it's like 1. We're not dealing with bytes here. We're dealing with an address that is a list of values and not a list of bytes. So it's just going to be plus 1 for the next item in this list here. So, and that one is going to be, you know, over here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be like 9 to 10, 11, 12, 13, 14, 15, 16, 17. So 17 or something like that. I don't know. There might be a one-off error on the ending part here, but whatever. So that that is the basic thing. And then this slice is going to be kind of returned. Well, it's actually, well, it's already stored in the result register. So this is going to be the code that kind of creates this string here, right? And then we're gonna push that when executing this thing. So actually, this will probably be made in the same thing here, same instruction thing. So actually, this would be like we're pushing we're just pushing or there. Okay. Actually, I think maybe even what's gonna happen here is because whenever we compile things here, R is very volatile. So R could very well be used up by this compilation. So what we could do is we can push R, and then we pop R, or we pop over here, which will store the thing in R, and then we just push the thing that was there from before. So we're pushing R here, which means this allocation, and then when we're over here, we pop it off so we store it back in R. So, and then we push it back. We could also have like kind of the convention that whatever we compile here does not touch like the outer R, but R is used for returning things, so that doesn't really work. So, and also it becomes a problem here because let's say this wasn't a read-only, so it's not as simple as doing this, right? So what's this gonna be? It's like, well, we're not really gonna have this R here to be used like this. What we are going to have is we're going to have it on the stack. So we push R here, which is kind of like Well, actually, we're gonna have a ref R, which is well, actually, it's gonna be like ref slice or whatever, or string literal, and then we're gonna set the ref, which is then gonna be, because we should have some kind of stack frame here, I think. So set, so this is gonna be like, well, I'm just gonna say stack frame. That's not a real instruction, but it's just gonna say that this is inside of a stack frame here. And so this is gonna set stack frame well, I guess it's like +0 like this, and then it's gonna set it to, so this is the first like local variable, I guess you can say. Well, this is this push here, and so that's gonna be well, yeah, it's gonna be like this. So alloc, so that's all. So we're storing the result of this into this ref here, which also, remember, if that ref also pushes things, so this will get put on the stack. It's just a labeled push basically, except we need to set it later, so we don't like provide the value here, we provide it later. We could also change ref to actually be like a push instead, or we can change push to be optionally labeled or something like that instead. But anyway, this is how we're doing it. So we create a ref which pushes space on the stack. We allocate to, which sets R to be whatever we allocate it to, and then we set the ref to be R. So actually, I'm gonna do like in parentheses. This is actually string literal. So now we can refer to this as the slice, right? Because then when we compile things in here, they could mess with R. So it's like we can't really use this to address to get to the slice. So we have to use like this now instead. All right. So first we're setting this to R, which sets the slice. No, hang on. Yeah. So this is where the things become tricky, because this is referring to the stack address. Like, yeah, we're accessing the stack address that is the result of adding stack frame +0. So that's the address where we want to store this, right? But here we want to go a step further, because this is an address. This is an address in itself. Well, it's a slice to be, yeah. So it's a little bit more complicated than this also, because this is actually like, it points to the heap where we have, or no, hang on. No, it's a value. That's right. It's a value that holds an address and length. But no, because I want, no. Yeah, it's gonna be what it's gonna be in the end. That's how I like did it at first. But how it's gonna be in the end is that this is gonna be a pointer to the heap. Well, it's going to be a struct. That's what it's going to be. So, but the struct is going to hold two values, which is the address and the length. And so this could be like copy by value. So this could be put on the stack, for example, which it is then. So this would be put on the stack. However, the thing is, it's not just one value then. It's going to be two values. So we're going to put R, but then R is not a value itself, though. How do we return? Actually, yeah, this is a problem. Like how? Well, okay, so this doesn't return the struct. It returns the address of where the struct has the address to. Well, it doesn't return a struct. Yeah, it just returns the address. Yeah, it doesn't return the length. The length is like known. We already have the length, so we could build a struct from here. So actually, this should be the address, and then +1 should be the length. So this would be 2, which we already, it's like hard coded, or yeah, we kind of know how long this is going to be. So it's going to be, so this together now becomes the struct. So this is like the slice address, and this is the slice length. So there's a slice struct kind of stored on the stack like this. This is the first field, which is address, and this is the second field, which is length. Okay, so now these two stack values together form the struct slice. Okay, I'm just going through this mentally, like the mental gymnastics in my head also, to kind of figure this out along the way. Okay, there we go. Now comes what I was trying to get at before. It's like, okay, now we have an address to where the slice is on the heap in the stack, but how do we now dereference that? Like, how do we dereference? First, we could do this to get to the value of this pointer, like here, but we want to dereference that again. So we want to kind of set that. Because it's like, yeah, we're accessing the address on the stack, but then we also want to kind of go one step further and dereference the thing inside as well. Now, I would think that, like, in a real assembly language, you would kind of use maybe another register to store that address, and then kind of dereference that register. And then you would use like a pseudo stable register to do that, like a register that's not touched by like normally, well, it's normally like restored by other expressions. Because the thing is here, like in between here, things are gonna get compiled. Well, okay, maybe we can determine where things are gonna get compiled. So let's say over here, let's say we actually do compile. Let's say this is compiling first element. Okay. So the result could be stored in the register. I guess what we could do is like check, is the result stored in the register? In the result register? If not, then we can freely use it, because it's supposed to be you should be able to use it. If it's stored in the result register, we could push it first and then restore it later. So in the end, we can push. We kind of saying that, hey, we're pushing this result, or it's like compile this, and this is gonna be like compiler code. If result is equal to, if result is stored in R, then we're gonna push R, and then we're gonna like say that result is equal to, and then whatever the address this was gonna be. So now actually this could be a ref, which would be like compile results. So this would be, well, segment result, and we're gonna set plus, now it's gonna be +2 to this, and then the result is then gonna be +2, so that is gonna be, you know, the ref segment result. Okay, but if the result is not R, it's, we don't actually do anything. We can just get the result. So result is equal to this. Okay. So now over here, so I'm gonna just separate this a little bit. So now over here we have the result from the compilation is stored in this result location, but R is also, now we can actually use R. So actually we can say set R to be the value at stack frame +0. So this is the address of the slice. So R is now the address of the slice. So now we can use the reference on R to actually get to the where the slice contents live. So now we can say +0 is equal to this, whatever is like, this is the result. Okay, and then we do a similar thing for the second. So this is for the first element, and then we do the same thing for damn it. What the hell? The same thing for the second element. So here's the second element. And it's gonna be the same thing. We store it. This is now 3. So we need another. Well, it depends. It depends if this was actually, you know, added things to the stack or not. But yeah. And then, I mean, I guess we could also like always push things so it doesn't. No. That's not optimized. Okay, but anyway, then we set this, or we get back the address of the thing, and now we set +1 because we are at the second element now to set the result. So this is how we could build up all of the, like, each element of this interpolation here. Okay, so we create a ref where the string literal is, we allocate stuff, we set, now we build up the struct. So we're pushing this there. Also, what's important here is that we should also set the we should allocate stack space for this slice. Right now the stack counter is like on. We're not really pushing this. Actually, this is just a push though. Yeah, this is just a push. What the hell? Yeah, there we go. We're just pushing those. So we're pushing like the slice struct here. Okay. And this would also be kind of like, this would be a push as well. Although this is the push, yeah. Yeah, whatever. Yeah. And the result is that if result uses R, then we push it and we set the result location to be this instead. And then actually it's the ref, well, whatever. And then this, no, yeah, that's the stack. Okay, whatever. And then we set R to be back to the string literal. So this is actually, well, this is going to be string literal, yes. So this is actually, this is like slice.address, and this is like setting, so this is like, hey, we set R to be slice address, and then this is like setting kind of like dereferencing R and set that to be the result. Yeah. Okay. And then we compile again, and we do the same thing here. We get the address, and then we add 1 to it to set the result on address like +1. And then, what do? We pop. Actually, you know what? Where do we actually pop this later? We should also like, we should have this if is yeah, we need to pop here if result was like originally R. We also do a pop here to get rid of this push over here. And then the same thing here. And now we should, everything should be restored. The balance, the stack balance should be restored. When we pop here, this should refer to the slice address. The problem here, though, no, we should push the address to the struct itself. So actually, we're gonna push this. We're gonna push like SF +0. But it's not dereferenced. So this is gonna be, you know, push the address, like it's gonna be like push string literal like this. It's kind of like, yeah, we're pushing the address of this. So that later we could say that, okay, how to access adder, we're having the first element, how to access length, we have the second element. Okay. All right. I think it's good there. Yo, borrow checker hasn't showed up yet. Maybe soon. Okay, so I think we should have everything we need for the planning. Now's the only part is like implementing this. So what are we missing here that we need to implement? In terms of like instructions and stuff. Like instruction types. So this kind of like setting the dereferenced location, that should be possible. I just need to double check that. And this should be possible, like referencing the dereference of this with modification to the address. And then same thing here. This is what we need to double check if we can. Same, yeah, nothing different here. This should just be like register with modification. Well, actually it's just register, absolute register. Yeah, and then the rest we should have. Okay, so well, also the thing is like kind of knowing how to evaluate this, because the thing is like, yeah, we're pushing like an address here, but how do we know how to then read that address to handle it in the execution later? So that's what we're gonna have to interpret this address as something. So I'm not sure how we're gonna do that actually, if we're gonna, because all like it's just an address, and then we're looking at this which just has like 2 numbers here. So but we don't really, it doesn't have a type that we can look at. Maybe we could try to embed that somehow in the thing. Because the idea here is that you would push a bunch of things on the stack. You would push the arguments on the stack. The first, or like the last here, because it's like reverse order because we're pushing to a stack. The first is like the executable like name, and then it's the arguments. But each push is one argument is the idea. I mean, there might be another way to do this, but that's the idea. And then this is the number of arguments. So exec would pop this. It would then pop this number plus 1. And then each argument will be put into a list and like materialized into a string. But the question is then, how do we actually materialize this into a string? Unless we automatically say that, okay, well, all of these are going to be like stream of strings. But what if we have, you know, another that is just this? Do we still convert that into... I guess what we could say is that if we just provide like an address, we can assume that it's going to be this kind of stream thing. If we have, you know, a data, read-only data or anything else, we handle that. But if it's an address, we always assume that it's going to be this type here. So that's what we could do. Okay, so what's missing from the compilation is this part. Basically all of this here. And then interpreting this is what's missing here. All right, so let's go and check that out. I'll probably do like a shorter stream today. There's a lot of things going on at work right now, so I don't have much time to, unfortunately, to spend here, but I wanted to do a little bit just to keep things rolling. Okay, so where are we? Compile string literal. Yeah, so here you can see that if we only have one segment, it's always going to be a string literal. So we just add that to our read-only data, and that's the result. But if we have more segments, then that means we might have some kind of... Then we need to compile the segments. which is gonna have interpolations in it. So here's the new ref, just like the. Let's actually bring this in here. Wait, it's binding, I think. Yeah. So yeah, the stack frame we don't really need to care about right now, but we're gonna have this ref here, string literal, and then we're allocating the number of segments in here. Okay. And then we set that no, hang on, this is wrong. This is wrong here. Man, I wish there was a way to kind of label, that we could label a push instead of creating refs, like, yeah. But okay. Yeah, so this is wrong because we want to set basically, you know, string literal. Plus here. I'm just gonna say this as like a notation for dereferencing to set the contents of this ref to the thing. But now that's the thing. Now we can push, because this only pushes one value, which we're setting to be the address. And then we push after that, right? Okay. So we're setting ref to be, I'm just gonna do that. That's fine. We're setting this to be actually it's gonna be like this, yeah. We're setting this to be R, which we are doing here. And then we also need to set, then we need to push the value, and the value is string literal segments length. Why does that break like that? Like, why does this break down when I do this? That's weird. Okay, anyway. So that was push. Okay, so now we're on to the loop here of these segments. Right. And here's the thing. How do we now, because I wanted to have like a way to kind of access fields in a struct in a generic way. So this part here, these things are, it's actually a struct. And then we want to access like fields on that struct, right? So what we're doing is we want to set no, not the field. Hang on. Well, this is kind of okay. So if we have a text, oh yeah, if we have a text, then we just have a read-only thing here. Now before we just set like a zig straight array here, but we need to do it in like the instructions here instead. So we'll check. Well, it's not going to be R, is it? So we're just jumping down here actually. So we're setting R to be the address of the of this ref. So we set R to be R. No, wait, what? No, we set R to be the slice address, right? So this is going to be the ref. I'm pretty sure that will, like, because it's a ref, it's kind of like dereferenced automatically. So it's going to set the contents of the ref into R. Actually, if we have ref, we could use that directly. Or do we have that anymore? I don't actually. Yeah, we do. Which is just gonna be this. And then when we evaluate a ref, we use this plus that. Although this could have. Okay. Well. Okay. This does not take into account the modification. We really should take into account the modification here. So what I'm gonna do is I'm gonna add mod here, which is like location. Wait. Mod, and then it's gonna be plus this, and then it's like location, and then it's like mod apply. Yeah. Can you have commas in here? No. Okay. Right, so now you need mod as well, so we can do location mod. There we go. Cool. All right. So that means actually we don't need to, like, we don't need this now, because this is just setting R so that we can dereference it later. But now we can just use ref directly actually. So let's remove this and we'll just use the ref. So this is going to be the ref address. Actually, no. Am I just lying right now? Let's go back. This is modifying. No, this is to the stack. Yeah. So that doesn't work. Okay. Well, we still want to have this because we want to use it as well. But okay, that does not actually work. We actually do need to set this because we do need to kind of, yeah, so that they did not dereference like twice. That's what I was thinking. So we're gonna have we're gonna need to set the R register to be ref. Well, that will set it to the address. Yeah. And then, so this is actually gonna be, we don't really need to do this. We can just say string literal here. Okay. But then we dereference. Well, this is gonna be dereference. So I'm gonna add this notation to kind of refer to this as like a dereference of whatever's in here, because this is a location that points to the stack, but then the contents of that location is the address that we want to put into R. So I'm doing this to dereference that, put that in R. Now we're getting the address of the slice. Okay, and then we dereference that address to actually set what the next like item is. So so that will be over here. And now we don't, well, I mean, we don't really need field for this though. We just want to do this part. So I'm gonna do, well, this is gonna be the results. Okay. And then it's gonna be like set. And then this is gonna be init mod or init add the location is register R, and then we add 0. Actually, this should be abs then. But then that would just be R. Actually, this is a dereference. Yeah. Dereference. Wait, we don't have dereference here. Okay, I'm gonna check how does that work. Like if we have R, we resolve a location. This just returns the value. It doesn't actually apply modification either. So I think the idea is that this would return a location. No, this just returns the contents of R, which then should be an address. So how do we dereference? We don't actually dereference here. That's the problem. What is my age? I'm like, I'm just below 40. What's your age? There was something weird about that. Like, I don't like questions like that. It's like, there was something weird I heard. You're not supposed to talk about things like that on stream or whatever. No, I don't know. I have no idea. I might be. I'm just playing it safe. I might be like mixing things up. But someone asked what my age was in the other thing. I'm not sure if it was like mentioning if you're like, or yeah, maybe it wasn't age, maybe it was something else. I don't remember. But there was something that even if you just mention it, you would get like banned or something from Twitch or something like that. These goddamn things. Okay. So I think what I want to do here is treat these as kind of like addresses, like values, because you can see here that we're having like from address, location, apply mod, thread, private, strike frame. So this is just a number that we just add or subtract to with this mod here. And then the same thing goes for this one. This is just a number that we do that for, and then we turn that into kind of like a value. But this one just reaches into the register, treats it as a value. So I guess that's correct. However, we don't actually apply any mod to this. So I think what we need to do, if this location has a mod, we probably need to also apply that mod here as well, because that would, I think, solve the issue. But then it's kind of like we need to, because this could be any value, it doesn't actually have to be a location. So it's kind of weird, because normally R would be like a register in a normal assembly would be just a number, but here it's like it's like a value which can be anything from, it's like a more abstract thing. So it doesn't make sense anymore to do that unless it's a location itself. If this is a location, we can apply the mod. If not, we probably don't. So maybe if we switch on it and it is a location, we get that out. And we say this should work here. I'm not sure why this is not working. Ah, because it's an address. That's right. Yeah, address. No, address cannot be a location. Although it could be. It can be a register. It can be a dereference. Right. Maybe I should have just gone with making everything a byte instead of doing all this. Okay, let's just, okay, let's see here. So what do we actually want to do? So we could have a register. Now this is kind of like a location. It has a mod and a thing. Then it's also, we also have the reference, which kind of the same thing, except we have an address as well. No, it's an address or a register. So let's say we have a dereference that actually does what we need. Actually, yeah. Let's only look for dereference. Dereference. Okay. So we'll keep the dereference. Type. And we're gonna have a, well, now this depends on if it's an address or a register actually. We could also add a convenience function here that like applies some kind of mod. So we would return switch on self. If we are an address, we return, actually, probably, I mean, yeah, it's probably more convenient if you return a value, but whatever. Address is well, we need to get the address here, and we need to say address mod apply. Okay, and then we have the register. Which could have, this has like a mod of its own. So it's gonna be like mod is equal to the original mod, but then abs is abs except, no, actually we need to kind of modify the mod. Also it could be, okay, if we have the mod, we do like merge with this. Wait, no, merge with this, yeah. And then otherwise we'll just grab that, yeah. We could also do this. We could do mod.merge reg mod, and then have the merge function be like take a nullable or optional, and this would return a mod. All right. So wait, is this even possible? Yeah, I guess it's possible. So it's like if, so const other is gonna be other or else return self. Okay, so that's the null case. And then it's like, well, if we are add, it depends on what O is. If O is like, if O is add as well, we just add. And I'm gonna call you X. So it kind of depends on the values here. If O is add as well, we're just going to return add X plus Y. If O is sub, now it depends what is larger. So if X is larger than Y, that means the add is larger than the sub, so we should still have an add X minus Y. Otherwise, we should have a sub of X. Wait, Y minus X, yeah. And I mean, it's probably, I mean, I could change this to be simpler as well. Like, let's just say we have add and this is an I size instead. But whatever. Okay, but these are that's the thing. Okay, now here's like the other way around. If this is a sub, it becomes easy. It's just X plus. Actually, it's sub X plus Y. You have to be careful here with the minus and plus. Yeah. Actually, this... No, that's correct. Yeah. And then add. So if X is larger than Y, let's do it the other way around. If it's less than Y, that means the X... No. Yes. That means that the positive, like the add, is more than the negative. So that will be an add. But now it's like X minus Y. So it's like a little bit other way around here. Otherwise, we're gonna have a sub, and we just flip this around, I think. So Y is the add, it's less than X, but it reduces the amount we subtract by Y. Okay, there we go. A little bit of inconvenient stuff happening there, but whatever. Okay, so this should now work here. So basically, if we have a dereference and we apply a mod to it, if it's just an address, we just apply the mod here. If it's a register, we will keep the register kind of type, and then also change the, like, merge the two mods together, because it could have its own mod. Okay. And what happens now? So if we have a dereference, we can now say dereference is deref, apply mod, and then location mod. But if it's anything else, we just return. I mean, technically it could be the register itself as well. In which case, is that, well, that's not a dereference, but we want to modify the register, I think. But otherwise, I'm just gonna add. I'm just gonna return whatever was the original here. So register. I guess if it's a register, we do want to do something here. Yeah, we could just apply mod. No, actually, we can't. We can. No, we just merge it, yeah. So register is equal to and we have apps. Mod is gonna be location mod merge. Oh, register mod. Oh, both of them. Okay. Right. Okay, I guess we could do this. I guess we can say question mark. Because then... Wait, would that still work? I'm not sure, but then we can say location. Well, I'm not sure. Actually, I don't think you can do this now. Because it's no longer like a member function. And you can't like have a member function on optional. So I think what we have to do is like location mod dot merge. Oops. Which of course we don't. Actually, it's gonna be IR. No. Okay, it's not exported. Okay. You know what? Let's just export it here. Okay, merge. Now there's going to be location mod and rate mod. Oh. Okay, let's just call it R then. There we go. Okay. So, right. So what we've done is basically saying that, well, now we can have a value or a location. If we get if we have the R register as a location, we also now modify with a modifier if it's a dereference or a register. And so now we can use this here. So let's see, the first one we set the register to be ref. So that would just set the register itself. Okay. And then this is the pointer to the data, read-only data. This is setting now. We want to set the register, but this is going to be like a dereference actually. But the thing is, this is a location, so that's the thing. It's a location. And given a location is not really, we can't actually dereference that. We don't have a way of dereferencing that. I mean, maybe we can have a dereference flag here. Hello, Subbugs. What's up? What's the language called? The language is called Runic. That I'm making, but the language that I'm developing in is called Zig. Like this here, Z-I-G. I'm just gonna refill my coffee bear a bit. Yeah, sure. Let's just add a dereference flag here. But then if we do that, what if we refer to the stack? Because then it's like it's ambiguous which address we need to add to. I guess it's like the result address. Well, no, the address we're taking, the first address we can modify. We do. And then we dereference that. No, that doesn't. No, that doesn't make sense. So we provide a register, which could be like R in this case. Okay. Oh, wait. We set it to dereference this. Yeah. But then this is like a, no, it's a value. That's right. This is a value. Yeah, okay. So actually this is the reference. Is this like a shell as well, or just scripting? Can this run the binaries? It's not a shell. It's just for scripting, and yes, it can run binaries just like Bash. Input out management. Yes. Well, the idea is that anyway. It's like not complete yet. So I can show you here. I usually have this little comparison. So on the right hand side you can see Bash, and left hand side is Runic. And so it's basically like Bash, or what you could say is it's Bash with different syntax when it comes to this like programming tools parts, or it's also, or you could say it's like Zig syntax with embedded, pipelines, executable or binary calls, sort of. It's a little bit more complicated than that because of how Bash works and how the pipelines kind of work, but I guess it's more fair to say it's like Bash with different syntax. Yeah, so here you can see, for example, you have a standard pipeline. Now, these keep in mind that these examples are not meant to be what's good, code. It's just to show what is possible. So it's not like this is a real example. It's just to have some kind of example to show what kind of things you can do. And just show off the syntax next to bash. So well, TypeScript is like, it's not really like TypeScript in the sense, well, okay, it's kind of like TypeScript for bash, if you want to put it that way. But it's not like compiling down to bash. It's its own interpreter and everything. So yeah, it has like, it's going to have like a type checker to check the types of everything. It's going to have it's gonna compile the actual code first before it runs, and the compiled code is like, it's interpreted, but it's not compiled to like a binary. It's compiled down to kind of like a intermediate representation language that is then executed in a virtual machine. But it's still, the idea is that it's gonna do everything that bash is doing, almost. Not everything, of course. There's probably gonna be a whole bunch of missing features, but it's gonna do kind of the basic things. It's more like, for me personally, to have a different language that I can use to create bash scripts in, because I'm tired of looking up bash syntax. So that is why I'm making this language. But it's also, I'm making it also because I'm interested in making languages, and I feel like I find it very fun and educational. So yeah. So and then it's also like kind of like a little bit experimental as well. You can see the functions here looks kind of funky if you're used to like normal functions in programming languages. You would wonder like, why do we have two types in here and stuff like that. And well, it's going to be an experiment on how the functions work, because in bash functions are how you say, they are kind of, I don't know, they kind of act like their own like executables or binaries, which is going to be the same for this. So basically what we're defining here is like standard in here and standard out. So it's going to be kind of like typed pipes. And so so let's say this, you call this hello, it doesn't take anything in standard in, let's say. So it's gonna say, hey, standard in is like cut off. And then the standard out is gonna be strings, so it's gonna output strings, and it's always gonna be streaming. So this is not actually like the return value, you could say. It doesn't return one value. It's gonna stream out a bunch of strings. That's what's gonna happen here, because that's how functions work in bash. That's how functions work in this kind of environment. And then you could potentially have other things here as well. Like if you convert a string to an integer, you now have a function that produces integers or something else, or structs or whatever. Hello, is the type checker working? It's like in a pseudo working state right now. The beginnings are like completed, but it's not like, for example, for functions, it doesn't check like standard in, standard out. There's not a check like that. But it does check if you're trying to assign a string to a variable that was originally a number. So you can't like it's not a dynamically typed language. It's a statically typed language. So if you set n to 5 here, you cannot set it to a string later. So that will become like an error. Also, we do have like an LSP as well, but it's everything is like in a kind of like a flux right now. It doesn't actually, yeah, it might work, it might not work. It depends on what I've fixed at the moment, and it might break at any time. So function is more like a transformer for types. I mean, I guess you could say that it's just like a normal function, except it's streaming. The result is always a stream of values. Instead of just one value, it's a stream of values. Because you could potentially, you know, output a bunch of things here. And also there's like a hidden, well, it's not really hidden actually. So this type is actually wrong. In the end result, we will probably have something like an error union type like this. So this would indicate that this could return some kind of error, because we are calling, you know, we're calling echo here, and we don't know if echo is gonna fail or not. So this could be potentially an error. And I'm not sure if what the result is gonna be, if we're gonna have like this type here, stream of string, to kind of put it in like a kind of like a monadic sense, that you would have like a stream of errors or string, or if it's going to be like this. Yeah, because it's probably going to be something like this, because you're going to be able to get, you know, some of these are going to work and some might not work. So let's say you have like cat, and then you add a flag that is wrong. So we are going to get some values, and then it's going to X fail here. So you would get like a stream of strings or errors. So it's going to execute until here and then fail. I'm not sure if we're going to continue. That's up for debate, but it's going to do this at least. You're going to get some strings out and an error. Is this language going to support libraries? So yeah, the idea is that you would also be able to import other runic files, which would kind of work like Python imports or JavaScript imports, which means that the imported file is working kind of like, you can have it act as a function itself, kind of like bash scripts as well. Bash scripts are like functions, but they also work as modules, because you can import a file and then access functions on it, or yeah, declarations on it. And so that's the idea. So let's say you have a function called hello in a module. If you import that module, you would be able to call like module.hello or whatever. But yeah. And then of course these, you know, basic things that exist in normal programming languages does not require special syntax like adding two numbers together. This is part of the string interpolation here, so you get this string interpolation syntax. But then this thing inside the thing here is just a normal expression that you can have outside here as well. I mean, you can have like, you know, my integer c is equal to my integer a plus my integer b. You don't have to have a special syntax to execute that. You have floats, which does not exist in bash unless you're using something like here bc, which can be used in bash to have floats. But normally you can't actually add, or floats are not supported in bash natively. But of course here it's going to be just, you know, used as normal here. And then here's some other mathy things where in bash you have to kind of I was actually surprised that this does exist in bash, but it's you have to surround it by double parentheses, but here you don't have to do that. Yeah, and some other stuff as well. So yeah, it's gonna be, you think about it like bash, but with like syntax from kind of like a consistent programming language like Zig. Yeah. and I will see what I can, you know, what I will add, because I will probably stop developing this once it's, we'll see though, I'm not sure, but it's, you know, anyone can contribute if they want, but because it's like it's available to on GitHub or whatever, and but I'll probably, you know, move on to other things when I get it up to the point where I can replace my bash scripts fully with this here. So it's probably not going to have all the fancy bash stuff in it, like everything that bash has, but it's going to have enough for me to be happy with it anyway. Yeah. Okay. Right, so floats in bash would be nice. One time I had to write an assignment on some statistical modeling and just faked it in bash by having two numbers and just printing dot there. Okay. So it's like bash plus plus. I mean, I guess. I don't know. I haven't looked. I know that there are other languages that tries to kind of do the same thing, or well, I'm not sure about the exact same thing, but that is taking like the idea of bash and tries to make another language that is like bash but different. But I haven't actually looked at any of those, just because I didn't want to get. I wanted to have no influence on this language. So there might be other languages that already, you know, do kind of the same thing. But I just do this also just because I want to make a language, and this was like an interesting idea for me, and it led me to some stuff that I haven't done before. So yeah, bash plus plus in double parentheses. Don't forget that. Yeah, I'm not really sure. I mean, Runic is the language, is the name of it, but it's like, I don't know. That also might change. I'm not sure. But I feel like it's a pretty cool name, so I probably won't change it. But yeah. Okay. Now, what do we do here? Right, we're setting R to the dereference of what? That's the problem we have right now. Like the ref, we don't really have the address, I don't think. I mean, I guess we could, or do we actually have the address? We don't have it compile time. We have to kind of use like the stack frame. And then ref is gonna be a ref, of course. Okay. Our comments / want that my shebang's impossible. Actually, right now it's both. So you can use whatever you want. You can use this, whatever. Wait, isn't it like this? You can do that. You can also do this. Right now, I'm not sure if I'm gonna keep. I mean, there might be a point in removing the // because then it's like, yeah, now we have like a difference between the languages, so it's more easy to spot that this is actually not like Zig or anything. It's like it's like runic. So that it does make sense if it's gonna be a bash-like language that the comments would be whatever the name is for that character, the square. Actually, what would this be? Because I think we have runic, yeah. So if we say this, oh wait, no, that's not correct. Wait, is it an alias? Or did I just put it here? Maybe. No. What? How do you check? Where did I define this? I don't understand. Did I add this as a path? Okay, well, let's just do this, I guess. Okay, so there you go. Are you using a compiler to generate the parser and the AST? I am. So, okay. So first what's happening is that this source code is being made into tokens through Elixir. So I'm not sure how familiar you are with this. These things, but basically this is the source code, and you can think about the source code as this. This is basically just a bunch of bytes, right? And then we put it through Elixir, which produces tokens. So this would become a token here, which is an identifier token, and then this would become a string literal token, and then it's pushed through to a parser, which creates the AST. And then in this case, this AST is like a call expression with echo as the executable, and this is the argument here. All right, yeah. And then so yeah, there's a little bit of history here as well, because before we actually had evaluation directly on the AST, but now I'm rebuilding the thing because we ran into some issues. So I'm rebuilding into an IR language. So here is where the compiler comes in, and this creates the IR language, which looks like, you know, kind of like assembly. So it turns this into like an assembly, a new language, like an assembly kind of type language. And then this is put into the interpreter. So interpreter, yeah. It sounded a little bit derpy there, but yeah, interpreter, which, you know, executes the thing. So this interpreter goes through the IR language. So it goes through, and the IR language I can show you here. Like if we so this is kind of the result of the IR language. These are the instructions down here. So this is turned into these instructions here. So these are all the instructions that is turned into here. And you can see we have different islands of instructions. We have like, and they are called sets. So this is set 0, which is kind of like the main process. And then we have a bunch of sets. Now these 3 sets are for standard IO. So they are kind of streaming standard in, standard out, and standard error of the main process. And then we have this island down here, which is for executing this function. So this is kind of, you can think of this as being run in a separate thread, because we've had some issues with like streaming data in the pipelines. So my solution was that, okay, we can create this IR, and we can make because we can just step through these instructions and then have a virtual machine keep track of what's in memory, what are the registers, what threads do we have, and so on. So we have virtual threads that we can create using this fork instruction. So we'll have a virtual thread over here, which jumps down to set number 4, which basically executes this echo hello here. Yeah, and that also makes it possible to have, and you can see the execution happening here as well. And that also makes it possible for us to have a debugger as well, so that we can just step through things. So here's like, you can step through all of these like instructions here to see what's happening in this kind of like very detailed level. And there we executed the thing and so on. And there you can see somewhere along here, you can see this hello coming out. So, and then we end, yeah, and we'll get some stuff happening there, but because it's like we still have some bugs and stuff, but yeah. The basic stuff is kind of in place. I'm just trying to, yeah, I'm kind of like, this is not complete yet. Like the IR is not really full complete. So I'm currently building that right now. And actually, right now, I'm trying to work out how to get these string literals working like this. This very, very simple expression like here, but it's kind of complicated when you have to run it through, when you have to make it work generically and also through this virtual machine in this assembly-like language. I have to build in a whole bunch of stuff for it. So that's where we are at right now. And yeah, but we do have, let's see, where do we have the things? Blocks. So this one is actually working now. So we have this block which echoes a bunch of stuff, and then we have a tail here which is kind of like blocking the, you know, it's blocking execution, basically, you can say, and it's streaming out data. And this grep hello. So this kind of showcases that we can have a block which executes a bunch of commands and then stream that through this pipe out to grep hello. If we were to execute these one at a time, you know, we would never get over here to grep out the result. And also tail, it's gonna you know, infinitely wait for this to exit, because it basically never exits, and so we would never get something out. But if we run this using this command here, we can see nothing is happening. Okay, so there's an issue there. That has to be like recent or something, because it's yeah, it used to work, now it doesn't work. It's probably because of some refactoring that I'm currently doing, or not refactoring, but implementation of something here. But yeah, it's probably something to do with this compile string literal here. Not really sure, but yeah, it should have worked. It did work before. This shouldn't work. This doesn't work. What else? I mean, basic pipelines do work. This shouldn't work because we don't have bindings yet. What could we test, actually? I mean, this one should... I mean, okay, this might have the same issue, though. What was this one? Grep? Yeah. Yeah, this does work. Okay, there you can see. It does work. So this demonstrates the streaming nature that actually does work, because if we were to kind of call this and wait for this to exit, it wouldn't work. It wouldn't actually output anything here. But it does output to grep, and it does like, so that means that we have streaming pipes, and that was like the huge issue in the previous implementation of the language. Is like, how do we make this work? And then also another step above that was the blocks, which should work, but it doesn't work right now, but it should work. This was also a huge issue, because it's like, okay, well, how do we actually step through this block to also at the same time stream the result out? And that's why, you know, we made this. I made the IR language, because now we can step through and create these virtual threads, which will, you know, fix this issue for us. Could you try to update server log? Yeah, see, I actually tried that, and it doesn't actually work. Like if we run this, and then well, let's actually do this. Let's open a terminal. We echo hello again. It has to be hello in there. Yeah, there you see. It does work. But it didn't work when I tried to kind of edit it here. If I do this, it doesn't work. I'm not really sure why. But yeah, it could be something with like WSL. There's something weird going on with WSL because I'm running through Windows. So they could be there's something weird with the notify system of the file system or something like that. But what if we, let's say we echo okay. It stopped working for some reason. I'm not sure what happened there. So did it only work one time or no? So it like once I opened it in NeoVim and then saved, it stopped working for some reason. I don't know, because it's something with like, I don't know, maybe NeoVim destroyed the connection somehow. I don't know. It might have something to do with WSL, because this probably doesn't happen in Linux. If I run Linux like natively, because I run it through Windows, so there's some issues there. But yeah, that was a huge blocker. This block here, this thing also was a huge blocker, but now we have it working. Except we don't right now, but it should work. So yeah. But yeah, and now we're dealing with this. So what I'm doing right now is I'm basically implementing heap allocations in the virtual machine. So before we didn't have the concept of heap, basically. Because if you wanna create a string like this, well, it's like, yeah, sure, we can add an optimization to say that, okay, well, if it's only a bunch of read-only data, we can actually concatenate it directly in, like this is com-time known, basically. So we could do that. However, I want to have the generic case as well, where we don't have, you know, we could, I mean, if you say echo hello like this should also work to get the thing. You know, so, but yeah, so this thing is gonna get stored as kind of like a slice structure on the heap. Well, actually, it's stored. Well, the slice structure, the description of the slice is stored on the stack, but the actual like allocation, like we allocate 2 segments. I guess this would be 3 technically, but it's like, let's say it's 2, 1, 2, and so that's stored on like the stack of the virtual machine. So we don't know the address to it, we just know it in the virtual machine. So this produces an alloc instruction, which is this alloc2 here, and then we're trying to do stuff with it. So we're trying to basically implementing heap, and also kind of like struct type values as well. Maybe it lost a file descriptor or something, no idea. Yeah, I have no idea. I just know that there are some issues with the file events system when working through WSL, which has caused a lot of issues when you want to have like watchers, for example. If you want to develop a web project, for example, and you have like this watcher running, and sometimes it doesn't work because of WSL, when it would have worked if you were running like Linux natively. I don't know if it's in this case. Writing the file name doesn't update macOS. Oh, I see. Yeah, maybe Tail has the file opened in some weird way, and when NeoVim does things when Echo like appends to it, it doesn't like break the pipe. When NeoVim does it, it does it somehow. I don't know. Try with capital F instead. Okay. Like this. Okay, that still works. What's the difference? Additional checks, like when the file is rotated. Okay. Wait, where is that? Oh. I wonder what's happening. Like, what does rotated mean? Like, does it actually remove the file? Or what's happening? But yeah, you wouldn't want to see this though. But yeah, I guess it fixes the issue. Oh yeah, because we're not strictly appending. We're like rewriting the whole file. It gets a new inode number. Okay. Oh, so the data is still there, but it's okay. And now it's like when we edit it like this, it actually did removed it. But if we but if we only added no, it's still inaccessible. All right. Interesting. Okay. Well, I didn't know that. You learn something new every day. And I have a lot to learn when it comes to Linux and the pipes and file system and all that. Right. Well, I don't really have much more time left, unfortunately. So I don't think we'll be able to solve this issue right now, but maybe it's for the best, because this requires some thinking and planning, I feel. The problem is with these like ways of having locations be dereferenced and all that, like that whole system is like a total mess right now. So maybe I should rethink that, try to make this more that I think also like right now we're kind of dealing with like with the set instruction is like the first instruction here, the first thing here is like a location, and then the second thing is a value, right? Which does make sense in some way, because it doesn't make sense that this would be a value unless it's like an address. But it's basically, in that case, it's basically going to be either a register or an address, which is going back to assembly. Is like that's the thing you have. Like you have either you're setting like a register or you're setting, I mean, move. Let's say you're moving like a register or an address. So I guess it does make sense in that way. And then also you do have like modifications like this, like dereferencing and adding, and there's even scale like times if you have, you know, plus, you know, things like this. If you're modifying like an array with each element is 8 bytes long, so you can have expressions like this as well. Yeah, we already went there. Dialog. Like this is this is kind of like LLVM, except it's my own IR thing that I made. So we already have all this, a lot of this stuff is already implemented. I'm just but the problem is that the values and the locations are like they were like organically grown from the start, but now maybe I'll look back and maybe I'll just make everything a byte stream, because right now the values are really, they are like it, the value, look at this. So here's the kind of value that you could use. in the IR language. It's like we have this void. They are all actually kind of simple. They are very simple values. So everything here is like you can actually serialize it into a number, or yeah, basically a number. Everything here can be serialized into a number, and that means we can also deserialize it as well. Which is good, because then we can, as you say, can IR be output as a file? Yes, it can. Now it can. It used to not be the case, but now we actually can do that, because everything in here is serializable. But what I'm thinking is maybe change this so that the value is like you can only deal with, I don't know, 64-bit values or something. I don't know. We'll see what happens. But the problem is with the dereferencing and stuff, like, because now what we need to do is I'm setting register R to be the dereferenced value of this ref here. This ref points to the stack, so it's kind of like a pointer to the stack, where we keep the address of the heap allocated slice. So this points to the stack where we keep the address, right? But here we want to set R to the address itself, yes, to this address here. So we're dereferencing this because we don't want the stack counter, or we don't want the stack address. We want the content of the stack address, which is this, which is this here. So that's slice.address, and then we want to dereference that and set the contents of that address to result, which is like calculated here. So the result is not that difficult to get, but it's this part here which I feel is the issue. Because of how this has kind of organically grown, and I've kind of tacked on some functionality when the need arose. I didn't really plan for everything from the start. So it's like right now we're at a junction where either we just keep going, or we could also try to think of a way to kind of rewrite some stuff. But because it kind of becomes an issue when trying to think about, okay, is there a clear path to our goal here? But yeah, if we look at this here, set R, we have set, and then init abs is like, this is a register R. So this is kind of like, yeah, we're gonna set R, right? So we're setting R to a dereference of what? Of the register stack frame, because we can't really refer to this ref directly. We have to say stack frame plus whatever relative stack address is on the ref, which we should have with this ref here. Is like, we create this new ref here. This is always going to be a ref where the relative stack counter is like it's calculated from whatever has been compiled before. Okay. Okay, and so stack frame plus this stack address that we should have, and then we add that to stack frame. Yes, and that's it. That is gonna be that. So that should be the address. So this should be correct, actually. It's a lot of things happening here. But then also we have set now we want to dereference the register and set that address to be the result. So we have the result here. The result is easy to get, but then we need to set here. But now the problem is that we don't really have a way to dereference the register at this point. So that's what we need to look at. And that is probably the last thing I can do now before I have some of the stuff that I need to do. Yeah, because this is kind of just referring to the register. This is like referring to the register itself, except we add 0. Does that automatically mean a dereferencing? So then we go to our evaluator, and we're going to go to set, and we're going to go to register. And if we get R, we just set this to that. So that doesn't really work. Is this looking at abs or what? Yeah. So I guess, I mean, technically, like, let's say we have a mod. So does that mean that location, set location abs? Let's say we have a mod. If we have a mod, let's treat it as a dereference. See, this is what I mean. Now we're getting into spaghetti land, because it's like we're adding these things instead of like fundamentally solving the issue. We're adding these. I mean, I'm adding these things here. But yeah, if it's a mod, we can assume we're gonna dereference this. So so what this is gonna do is we have a value. We also have resolve location as well. Yeah, I guess we could just make a location, which is the register plus the thing. Yeah. So if we have location mod, we're gonna resolve the location which gives us like a value, but that doesn't help actually. Well, it kind of helps because we get an address. This doesn't help though. And see, this is the problem when working with this, because if we made the assembly language like have the values just be numbers, this wouldn't be a huge issue. We would just have a couple of different scenarios, but now we have like a whole bunch of different things that could happen. Where's no, it's set. Okay. So what do we need to do? We need to Once we resolve the location, what we should have is a register value. Yeah, so this kind of assumes that actually, yeah, the result register is a location. Yeah. Or an address or something. Or init, just init. Okay. So we have that. So that would now be the location, and then we should have, so, and that, yeah, that gives us a value. Hello Vicent, welcome back, what's up? And Cool Man, hey. I'm probably gonna quit here once I've either in like, I don't know, 10 minutes, or if I solved this issue before. Oh, it's a raid. Oh, thank you for telling me. Thank you for the raid. Let's see. Who is raiding? Kovi Man. Oh wait, I got 2 raids. No wait, that's 5 days ago. Okay, thank you, Kovi Man. I'm trying to solve an issue here with my kind of assembly-like language, almost. And yeah, is the language ready yet? It's, I mean, it's shaping up, but it's not. I wouldn't say it's like usable right now, but soon it might be. So. I just need this IR to kind of get, well, okay, it is kind of usable if you're using the what's on the main branch right now. You can actually use, I think, yeah, you can check out, well, I can show you this. So here's like, in the main branch, this file should, everything in here should work. So you can check out this MVP RN. That should work. So here you can see, like, on the left hand side is the runic language, and on the right hand side is bash. So you can kind of compare the two. And every statement here should be exactly the same. And then I have like a comparison script that like runs both and checks that the output is the same. So I kind of use it as like a test suite to see that everything is working as well. And keep in mind that all the things in here are not meant to be like good code or anything. It's just to kind of demonstrate what features are available and check that everything works, basically. But it's like demonstrating what you can do. So yeah, as I said, like everything in this MVP file does work. So we have you know, executing executables or binaries. we have basic like pipelines like this. There's no redirections yet, and so that might put a hamper in a lot of what you want to do, but hey, it should be there in the future. And then of course we have like if and else, like this, inline for loops with ranges. Yeah, same thing here. And then we have like functions are kind of strange, but they do work, but you have to kind of format them like this basically. Although this is wrong, so I'll just remove that. Yeah, bindings. Of course, you have you can have constants and mutables with var, and string interpolation. If you have if you bind something to an executable call, you can also access like standard out, standard er, and exit code through echo result dot, and that will give you the corresponding thing. Or you can also coerce it like this. That will be the standard out. Okay, and here you have like arithmetic is done through just a normal evaluation. Like if we take the equivalent here in bash, you can see that if you want to do arithmetic in bash, you basically have to kind of surround it in double parentheses. Where here you don't really need to do that. You don't. It's just a normal programming language. And of course we have floats, which does not exist in bash natively, but you can use something like BC to execute some stuff like this, which of course you can do in Runic as well, because we're using the same, you can do that in Runic as well if you want to have even more, I guess, calculation functionality. Compound assignment, which is a new word that I learned, and here we have all these different expressions that I was actually surprised that it does work in bash as well. However, you do have to surround with double parentheses. Okay, and then we have booleans, which is also very interesting because basically booleans are not really like true or false. Although it's kind of true is like it's a defined value or a keyword that does mean true, and false does mean false. But the value type that can be more things as well, because the value type is actually like an exit code. So in bash, it's like true is actually 0 and false is 1. So true and true is like, because if you compare this to C, for example, where it's the other way around, true is 1, false is 0, and you do and, it's like the logic table actually gets flipped around, or it gets like inverted. So it's like 0 and 0 actually becomes 0. 0 and 1 becomes 1. So, but it still means the same thing. It still means true and true is true, of course. True and false is false. Yeah, but then it's like if you want to echo this out, you have to kind of do this. This won't produce like you can't really like turn this into a string like directly. It's not coerced. So you have to do this to actually like get it out in a string format. While in Runic you don't have to do that. You can just say true and true, and that will coerce into 0 or 1 depending on what it was. However, it's kind of interesting because it's actually the value can be something else, like the type is not a boolean per se, it's more like an exit code. So that's, I kind of find that interesting. And here the last thing we have here is like arrays. So here's like arrays in bash, and you can iterate through them like this, And here's the same thing in Runic. So we have an array here, zig-like syntax here. And then you simply say for my array, which loops through all of the items in the array, and you capture the item like this, just like zig, and then you can echo it out like this. And then if you want to have, you can have like the iterate or the index. You put my array and then 0 dot dot. Just like in zig, you can have multiple, like 4 sources, as I call them. And then these are the elements of each iteration. So you get like item and I, like this. And in Bash, you actually have to loop through the length of this, which is it's nice. I didn't actually know you can do this, but this is very simple. You have like the array. I'm not sure what this syntax means. I read it somewhere, but I don't remember now. But it's something to do with arrays. And then the bang means length, I think, because we're looping through. Maybe, yeah, I don't know actually. And then, or maybe it means like turning each into an index, like each element. Okay, anyway, and then, because you can't have multiple sources in Bash, so this would be the equivalent here. And then you would do like I, and then you have to access the element I. So technically there is no equivalent to this, although you could technically say that this is the equivalent, but whatever. And then you have this, which demonstrates that you can have several arrays or several like iterators or iterables here. So my array 2, and then an index as well. And then of course in Bash it's like it is pretty simple. Like you just have to index the arrays to get the elements. So, which of course you can do in Runic as well, but doing it like this is good as well. And then you can, but also it has to be the same length. So these two has to be the same length. So I guess that's a difference between Bash and this language here. But yeah, that is basically all the features. At separates into shell words. Okay. I'm trying to think like logically, what does that even mean? But I can't do it. So does that mean it like separates into quoted values, like, you know, 1, 2, 3, like this? Or maybe it's not quoted, I don't know. Like this. I don't know. I have no idea. But what does this mean? That was my question. Like, what does this mean? This here. Think of it as taking a string ABC separates the actual ABC. Right. Because, okay. So it's kind of interesting, like, is my array an actual array, or is it just a string with like space separated values? And can you set like IFS to something else and it will be separated by something else, or is that how it works? Or how does it work? Because that is actually kind of interesting, because it means that you can turn anything into an array, although it also is kind of weird as well. Because it's like, then it's like a lot of string manipulation you have to think about if you want to take like the result of one command and turn it into an array. But yeah, it's very interesting. Like, Bash is a very interesting language, and I don't really know too much about it, but I know that I don't want to learn it, so that's why I'm making my own language to do the same thing, almost. It's an array in Bash. We can treat it as a string with star. Okay. All right. Okay. Cool. yeah, that's basically it. And yeah, right now I'm building the I'm kind of rebuilding the language from basically evaluating the AST directly, and now I am instead compiling the language into an IR that you can see here on the left. Is kind of like a sketch of the IR, and then I'm interpreting the IR language instead in a virtual machine that can spawn like virtual threads to stream data and do that kind of stuff. So we can kind of enable all this functionality the way I see it. So yeah, basically both a beauty but also a beast. Yeah, Bash is very interesting. I mean, I'm gonna have to learn some of the things in Bash to be able to kind of, you know, because the idea of Runic is not to kind of create. Well, it's kind of also, it's gonna, you know, work a lot like Bash, because I'm like, if you have a pipeline in Bash, it should work exactly like a pipeline in Runic, basically. So I mean, I can demonstrate the way I had before here, the grep thing. So here you can see we have, this is in Runic, so you have tail F, capital F, and server log. So this thing will kind of block, and it will output the things in server log. I guess the tail of server log, and then it would output to grep hello. So we can demonstrate that this actually does work right now, but I'm gonna use the IR. Actually, it does work for the normal thing as well, I think. No, it doesn't. Okay. But let's enable IR and it will work, I think. Yeah. So you can see that this command it's like blocking, but it's also outputting stuff into grep. So what we're doing is we're spawning up both of these and then piping the data through. Yo, Penguin, welcome back. I'm gonna quit here in just a second, but glad you could make it. Yeah, so this demonstrates that it actually does work for these simple kind of examples. And I think maybe the MVP, I'm not sure if MVP actually works for, it does work. You can see it's kind of slow, and I think that's because well, for one, the language is not built for performance, but two, I think it's because of how we map like the environmental variables or something. Yeah, there's a lot of optimization that can be done, but this is the old interpreter. The new interpreter will, I can't promise that it will be faster, but it probably will be faster. Well, it will be faster at some point anyway. But yeah, the MVP does work, so that's great. Okay. Yeah. So let's see if I can just figure this out here. I'm not sure if I can actually right now. Okay. So what we're trying to do is we're trying to set the dereferenced address that is residing in the register or to something else. And here's that thing. And then we're saying if we have a location modification, then that means we need to think about this as an address that we want to dereference. I'm just gonna do this to make it. You can see the indentation level is kind of insane here, but Okay, so that's if, and then we have else over here. All right. Okay, so we have the location. So this would be the location that we're actually trying to set, I think. But it's a value, but we know that it's gonna be a location, which is either gonna be like a dereference or a register. Yeah, dereference or register. Man. Okay, so what doesn't make sense here actually is that the value is a dereference. It should be the location that is a dereference, not the value, I think. Because it's like you're talking about, well, I guess it could be this. I guess it could be both. Because we want to dereference the target, but we also want to dereference the location. I guess if we had another register, we could also do like set, I don't know, R2 to be this. Or yeah, deref, the deref of R. And then we said R2 no, god damn it. Yeah. So what's happening? Okay, what's the happy path here? We have R that we have a mod for. So we look into the like what is in R. R should be what is in R at this point? So it's going to be this here, the address. And that points to the heap. So it's somewhere, it's like a pointer to the heap somewhere. It's just an address. Yeah. So it's the ref. No. We're setting. Yeah, we're setting R to be the value, and the value is the dereference of the thing. So it's like when we set it to this value, we also, if it's a deref, we need to actually deref it now. Yeah. That we're not doing that either. Okay, yeah. This is there's a lot of things not happening here, and a lot of things that should happen here, and I think I need to kind of rethink this a little bit. How we're dealing with addresses and dereferencing and all that. Because right now it's like spaghetti squared or cubed. So yeah, I need to fix that. But yeah, I don't have more time now, unfortunately, so we're gonna have to continue. Maybe tomorrow, we'll see. But yeah, thank you very much for joining me here, and hope you have a nice day, and I'll see you later. I guess I can send you off somewhere, because now we have some peeps in here. Rage. Yeah, no problem. Thank you. Let's do... well, this seems good, maybe. I don't know. Alright, let's send it here. There we go. Where's the thing? Okay, there we go. Alright, see you later. Bye.